Hello, everyone. Sorry for a slight delay. I had some internet connection problems. Let me know in the chat if you can hear me. If anyone could just write a message. Okay, that's fine. Yeah, so let me introduce myself first. My name is Michał. I'm a software developer here at Ethworks. I've worked on multiple of projects related to blockchain. For instance, I worked on ecosystem developer tools like Waffle or Hardhat. And today I'd like to give you a more technical presentation on Ethereum. So the previous presentations were more high-level introduction to the concepts that we deal with in blockchain, and in this presentation, hopefully, I'll clarify some more technical aspects. So without further ado, let me start. First, in order to talk about Ethereum, I need to first say a few words about blockchain. So this presentation doesn't assume that you know anything about blockchain, but it assumes that you have some technical background, that you understand some IT related terms. So what is a blockchain? A blockchain for a programmer or developer is yet another database. But this database is different than any other that we have. The main differentiating factor is that it's decentralized. So blockchain is a database that is not only distributed, it's also decentralized, which means that no single entity control it, and everyone has equal rights when writing and reading from this database. The way it's done, it's based on a peer-to-peer network where many computers distributed around the world collectively maintain the database. There are many different types of nodes in this network, but some of them hold all of the data that the blockchain contains, and these are called so-called full nodes. Other nodes are called miners, and these are also responsible for writing to this database. More on that topic later. What else can we say about blockchain? Blockchain is a public transaction ledger. It means that it records transactions just like any other database. A data structure that is created inside the blockchain is a linked list of blocks. That's where the name comes from. We call it a chain because this list is immutable, which means that you cannot change data that was added in the past. And obviously, there's no central administrator because it's decentralized. Blockchain can also be viewed as a state machine. So you have a genesis state, which in case of Bitcoin, we can think of it as balances of all of the accounts. And then you have a bunch of transactions, which can be seen as, for instance, transfers of cryptocurrency. And when you apply those transactions, you get a new state. What's important here is that you only get a new state after applying all of the transactions that happened in a single block. There's nothing in between. We only care about the states at the given block height. Other blockchains than Bitcoin, for instance, Ethereum, make the notion of transaction more general. And in Ethereum, you not only have transfers of digital currency, in Ethereum, you can program any logic that you like, which basically means that you can create smart contracts and your own state transition functions. I mentioned that a blockchain is a linked list of blocks. So, and I also mentioned that it's immutable. Immutability is possible thanks to a special function, which we call cryptographic hash function. And let me first remind you what are the properties of this function, because it's used everywhere in the blockchain, in blockchain domain. So hash function is a function that, given an arbitrary length input, produces an output that looks random to humans, and it has special properties. So the first property is that it's deterministic. Given an input, you always get the same output, no matter the time that you're invoking the function or the context. Another important property is that it's one way, which means that given the hash, so the output of the hash function, it's hard to determine the input. Here, the example with two colors mixing is intended to give you some intuition. So when you have a mixture of two colors, it's hard to know what were the input colors. Yeah. Another property of a hash function is that it's collision free. So it's very hard to find two inputs that produce the same output. It is physically possible, but it's so improbable that we assume it's not possible. Also, another feature is that even the slightest change of input produces a completely different output. So you cannot based on the similarity of outputs, say that the inputs were similar as well. It's not the case with a hash function. So given such a strong cryptographic tool, you can build an immutable chain. Immutability is preserved in this way that you hash a header of a block, and you store this hash in the next block. This happens for every block in the chain. This way, the hash that is stored in the latest block is sort of a hash of all of the previous blocks. If anything changed in block 38, the resulting hash that is stored in block 39 would change, and so on. This is how it's done. Mateusz mentioned in the comments section that you can ask questions and raise your hands on Hermit. At any point in time, feel free, and I'll be happy to answer some questions. We have two models of blockchains. The first one is called account model, and the other UTXO. Ethereum uses account model, which is easier for humans to understand. So we have accounts just like your bank accounts, where you have some balance, and then transactions are transfers of money from one account to the other. You store not only the transaction data, you also store every intermediate state. This is the case for account-based blockchains. In Bitcoin, you don't store the intermediate states. You only store transactions. So in order to get to know how much money I have at a given point in time, I need to go through all of the transaction history for my account from the genesis state. This is the main difference between those two models. A blockchain, in order to be able to deliver this decentralized feature, needs a consensus algorithm. The main point of this algorithm is to help nodes determine a common state of a blockchain, because you have a database that multiple actors can write to. We need a way to tell what is the common state among all of the actors. The second necessary feature of this algorithm is that no single node of the network can dominate building new blocks. So no single node can take control over the network. And an algorithm that was proposed by Satoshi Nakamoto in the original Bitcoin white paper is proof of work. And this is essentially what we use up until now in many blockchains. In this slide, I'll try to briefly explain how technically proof of work works. So the diagram that you see here is what a miner node does, how he operates. So a miner first listens for transactions that are distributed in this peer-to-peer network, and chooses transactions to be included in the next block. So he tries to add a new block to this existing chain. When he picks transactions, he then needs to solve a computational problem. And after he does it, he is only allowed to add a block to the blockchain. Why solving such problem? Well, this makes it less probable that two miners will arrive at a new block at the same time, because it's time consuming and you need to burn a lot of computing power and energy and money as a result. And as I said, it's not very probable that two miners will arrive at the same solution at the same time. So in order to what this problem is about, this problem is about calculating a hash function that has a number of zeros at the beginning. What does it mean? So I mentioned that it's hard that hash function is one way. It's hard to get the input that produces an output that you would like to see. Therefore, in order to get an output that has many zeros at the beginning, you essentially need to play a game of trial and error. You randomly choose data that you set as input and hope to get an output. In this case, the input is the block data and an additional field of the block, which is called nonce, that you choose randomly. This nonce was present here in the block header. You do this in the loop. After you arrive at a solution, you immediately show off to other nodes in the network, and your block is added to the blockchain. The algorithm managed to choose a single person that will determine the next block for the entire network. In case while you're doing this computation, someone else arrives at the solution, you need to stop, because the block you're trying to build is probably consists some of the transactions that were already added. You need to basically start from scratch. If you have any questions regarding this algorithm, feel free. I'll try to answer them as we go. Now, what is this algorithm for? Well, it solves a problem that is called double spending, and this slide will try to explain this problem. Assume that we have a blockchain that has 50 blocks so far, and we start our experiment from here. We have a buyer and a seller. A seller will offer some digital good, which can be bought using Bitcoin. At state B, the buyer creates a transaction that sends Bitcoin to the seller. He announces this transaction. It gets picked up by some miner and included in the block number 51. Let's assume that the buyer is also a miner, and at the same time, he starts building his own version of the blockchain, but he doesn't show this version to the rest of the network. In his version of the blockchain, there was no such transaction that transferred money to the seller. Then at state C, we have another block built on top of the block 51. The seller assumes that he got one confirmation. It's enough to trust that he got the Bitcoin, and he will send the digital good to the buyer. Buyer at the same time still builds his own version of the blockchain without this transaction. After he receives the digital good, what he does is he publishes his version of the blockchain. And now here is a rule that says that in blockchains, the chain with the most blocks is the one that we choose as the current chain, the chain that is the real thing. Such situation is not possible with consensus algorithm like proof of work, because how would the buyer be able to outrun the rest of the network? In order to do that, the buyer would need to have at least 51% of the computing power of the network. This is so-called 51% attack, and so he would essentially need to have the majority of the computing power of the network to be able to produce the results of this computation fast enough to outrun the rest of the network. In practice, this number is a bit lower. It's not 51%. It's somewhere around 30, I think. But this is enough for a decentralized network to operate. Obviously, people came up with different consensus algorithms. To name a few, we have a proof of stake, proof of authority, capacity, and elapsed time. I don't have time to talk about them all today, but I can mention that proof of stake is a family of algorithms that will have more importance in the future. Ethereum 2.0 will have consensus based on proof of stake. Okay, after this introduction, we can dive into Ethereum internals. So first things first, what are the main features of Ethereum? It's a relatively new thing. It was proposed in late 2013 by a programmer named Vitalik Buterin. The development started briefly after, and the first mainnet block was mined on July 30, 2015. So as you can see, Ethereum is only like 6 years old. It's still, I think it's still a relatively new system. It has consensus algorithm based on proof of work. It has its own cryptocurrency, which is called Ether. And Ether is divisible down to 10 to the power of 18 Vey. So just like in dollars, you have cents, one Ether is 10 to the power of 18 Vey. Ethereum is an expansion of Bitcoin in the sense that it can handle more complex smart contracts. And in order to do that, it implements Turing-complete and deterministic virtual machines. Now I would like to start talking about Ethereum internals, Ethereum data structures, and stuff that you need to know in order to start using Ethereum as a user and also as a developer. So let's start with the world state. What is the world state in case of Ethereum? So in case of blockchain, you could say that the world state is how many. In case of Bitcoin, you could say that it's how much money each account has. In Ethereum, it's a bit more information. But again, you have accounts which have addresses. Now we have two types of accounts. There are some accounts that are controlled by users using their private keys. And there are also accounts that are controlled by smart contract code. I noticed a question. I think we will publish this presentation afterwards somewhere as PDF. Going back, both of these accounts have a balance, which is how much money it holds in Ether. And also they have a field called nonce, which is a transaction counter, which means how many transactions this account made so far. Notice that there is a nonce name collision. This nonce here is something different than the nonce you saw in the block. Contract account also has the source code that controls it and a storage that you can write data to. So again, the same thing on a different slide. You can see two types of accounts. Only externally owned accounts are controlled by people or machines that hold private keys to them. Now, how do you get an address of an account? In case of externally owned accounts, you have a private key from which you derive public key, and then you hash this public key and take 160 bits of this hash, and this is the address. So the address of an externally owned account is derived from its private key. In case of contract accounts, because each contract account is created by some externally owned accounts, the address of contract account is a hash of some externally owned account, and this externally owned account's nonce. So for instance, if my account creates some contract account as the first transaction, it will be the address of my account and nonce 0. Then you hash those two informations and take 160 bits. Is the address of the new contract account. There is also one other way to create contract accounts in Ethereum, which is called Create2. But I'm not gonna cover this topic in this presentation. Now let's talk about transactions. Transactions can only be sent by externally owned accounts. So if you ever heard about something happening automatically on blockchain, that smart contracts talk to each other without some external interaction, it's not true. Every interaction in blockchain is triggered by some external actor. It obviously can be some service that holds keys to the private keys. It doesn't have to be a human every time, but it's always triggered from the outside. So an external actor creates a transaction, and we have two transaction types. The first type is contract creation. It's a transaction that creates a contract account, so it creates a smart contract. The other type is called message call, and it's a type of transaction that, for instance, can invoke some method of an existing smart contract. So here you have another slide that shows that a transaction containing initialization code can create a new contract account that has its source code and its storage. A message call, on the other hand, can, given some input data, update the storage of an existing contract account. Now I would like to show you a couple of slides that help understand those two types of accounts more. So imagine the blockchain system as a circle. You have green external accounts on the border of the circle, and the contract accounts in the middle of it. only the green circles can be entry points to the system. So you have different types of transactions. The first type is a normal Ether transfer between two externally owned accounts, just like transfer of Bitcoin between two accounts in case of Bitcoin. Then you can also call a method on a smart contract. You can also have a smart contract doing interaction with other accounts. So for instance, you can call some smart contract which will in turn send some Ether to external accounts. You can have a logic that is more complex than that, and I guess we can have a smart contract that creates a chain reaction. It calls a couple of different smart contracts which can in turn call externally owned, send Ether to externally owned accounts, and so on. Now let's talk about transaction fields. So this is these fields, at least a couple of them you need to know, because you specify them when you send any transaction. For instance, using MetaMask, which I will talk about more later. So every transaction has a nonce, and in this case, this is the nonce of the account. So if it's the first transaction that I make, the nonce will be 0. Or 1, I'm not completely sure, but it will be the first nonce, yeah. And then we have two fields that I'm gonna talk about in just a minute. Then you have the recipient address. You have the value of Ether that you are sending along this transaction. It can be 0 if you don't want to send any Ether. Then you have 3 fields which together make up the digital signature of the transaction. And that's why you don't have a field called from, which means the sender of the transaction, because you can derive the address of the sender from the digital signature. The last field is called init or data. It depends on the type of transaction that you're making. If you're creating a new smart contract, this field is called init. If you're calling an existing smart contract, it is called data. By the way, each transaction obviously is signed using the private key to your externally owned account. As I mentioned before, contract accounts don't have their private keys. They are controlled by the code. That's why they cannot initiate transactions. So smart contracts can only call other contracts in a transaction that was initiated by an externally owned account. So all of these arrows that you see here are a single transaction. Let me now introduce you to the topic of gas. So in Ethereum, gas is the unit of cost that the network needs to make to handle your computations and to store your data. So each transaction costs some fee that is collected by the miners. So there are 2 incentives for the miners to even take part in this proof of work algorithm that I talked about. The first incentive is the popular mining. So you mine a new cryptocurrency. You mine with every block. The miner is allowed to create a new transaction that will give him some cryptocurrency that wasn't present before. So he mines new coins. And the other source of income is transaction fees from all of the transactions that are included in the block. In order to calculate those fees, we need gas. So every operation that is done on blockchain has some predefined cost. Then you sum all of those operations, and you get an amount of gas that was used by a transaction. To calculate the transaction fee, you multiply the gas used value by some gas price. It's similar to normal gas that we used to power our cars with. You need an amount of gas to travel some distance, and you pay some price for this gas. To get the price of the journey, you have to multiply the price of your of the gas by the amount of gas used by your car. Yeah, so it's pretty easy to understand this concept. Now, what may be interesting for someone new to blockchains is that you yourself set the gas price. With every transaction that you send, you specify the gas price that you want to pay for this transaction. Okay, so why don't you just set the gas price to 0 and have transactions that are free of charge? Well, you need to know that miner earns by collecting the fees of the transactions. So at any point in time, there are more transactions in the network than can fit in a single block. So what the miner does, the miner first sorts those transactions by the gas prices, and he picks up those that will give him the most fees. This is like this is the way the majority of miners work on the network, unless you have some philanthropic miner that mines transactions for free. The amount of gas price that you need to provide, or the price of the gas that you need to set, is not something that's set in stone. It changes. You have a market. You have an open market where you have the normal economic rights of demand and supply in action, and the price changes every day. You need to keep track of this price and set it in a way that will let your transaction be mined in some reasonable time. Thankfully, we have tools that do that for us. We don't have to worry too much about it ourselves. Okay, so the next field that you are setting yourself is gas limit. Gas limit is simply a field that lets you limit the amount of gas that will be burned. So using gas limit, you can calculate the maximal transaction fee that you will pay for a transaction. Why would you want to limit that? Well, assume that you're calling a method on a smart contract that has a loop in it. Let's say for some reason this loop or this smart contract has a bug and this loop is unbounded. In this case, such transaction could drain all of your funds really quickly because it goes into a loop. Gas limit is a field that lets you prevent that situation. Well, in the real life, you wouldn't lose all of your money in such case, because there's also a gas limit to a block. So a single block cannot contain more computation than some amount of gas. So you would eventually hit the block gas limit. But anyway, you can also individually set gas limit for each individual transaction. You may be also wondering, how do you know what gas limit to set? Well, in case of normal Ether transfers, it's predefined. It's 21,000 gas. In case of smart contract methods invocations, again, we have tools that help us. Those tools simulate the transaction that will happen in the blockchain, and take the result of the simulation and set the gas limit accordingly. It's not so easy task, because sometimes you can have a logic that changes over time in the smart contract, and the time you make the simulation is different than the time the miner actually runs your transaction. But it's still better than guessing. Every transaction in blockchain is atomic. So let's say you have an error happening inside of a transaction. If some state change was made before that error, this state change will be reverted because transaction is an atomic operation. It's either all complete or it's reverted and has no effect on the state. Transactions are never executed in parallel, which can be actually mind-blowing. So you have a global system called Ethereum, global computer run by thousands of nodes in the peer-to-peer network, and you only have one thread. You only execute one transaction at a time, one after the other. So this is the case currently in Ethereum, and it's probably one of the main reasons we have scalability problems in Ethereum, which we try to solve with rollups and Ethereum 2.0, which is much wider topic. I don't have time to cover right now, but you can imagine where the bottleneck comes from. It's not guaranteed that you will get your transaction before someone else. So even if you send your transaction first, it's still possible that someone that did it after you will get his transaction mined first. Well, why is the case? Why is it the case? It can be the case of simply geographical location. So you need to bear in mind that you are sending a transaction in a peer-to-peer network, and the miner can be in totally different location. So assume you're in the United States, the miner is in China. Someone else sending transaction from China can be closer to the miner, and this way his transaction will be noticed first. And I've noticed that we have some questions in the questions tab. I'll try to answer them after I finish this section. So vote on the ones that you want answered the most, and I'll tackle them in a minute. Order within block is determined by the miner. I already mentioned that. So the miner sorts the transactions by the gas price, and he is in charge of the order. Order between blocks, so which miner gets to mine the next block, is obviously determined by the consensus algorithm. In case of Ethereum and Bitcoin, it's proof of work. Okay, so let me look at the questions. Has blockchain ever been hacked? Okay, so hacking a blockchain is a very, very broad term. And obviously, we have multiple blockchains. If we're talking about consensus algorithm, so has anyone been able to hack proof of work? Yes, it is possible, especially in networks that don't have a lot of nodes. So in such networks like some other cryptocurrencies that are not so popular, which are simply forks of existing blockchains, it's totally possible to get 51% of all of the computing power. You essentially can hire enough machines to join this network and gather enough computing power. In this case, 51% attack is possible, and someone could double spend the same money or do other malicious activity. It happens. I don't think I can give examples right now, but it definitely happened in less popular blockchains. What's important though is that it doesn't really happen in Bitcoin or Ethereum because those networks are highly decentralized and have thousands of nodes taking part in this competition of proof of work, and it's enough that we assume that it's not possible to hack proof of work. There's also the topic of hacking smart contracts, but that's whole domain of different attacks, and I don't think I have time to cover this right now. There's one question about EIP 1559. I don't think I can answer it right now because I only heard the news about it. I didn't read through the spec yet, so sorry, I'm not capable of answering this right now. Is it possible to move Bitcoin from proof of work to proof of stake to increase the scalability? Well, in principle, it is. It is possible to move from proof of work to proof of stake, but this will require everyone moving to this new network and everyone updating their software. So you can imagine that with such move, you will have a fork, and you will end up with a Bitcoin on proof of stake and a Bitcoin on proof of work, because not everyone will move. So such changes to the protocol consensus need to be well thought and planned in advance, and this is what Ethereum is doing right now. We are having a trial network of Ethereum 2.0, and there will be a modular approach to this, where current Ethereum network will be connected as one of the Ethereum 2.0 subnetworks, so to say. So this is my answer to this question. I'll go forward with the presentation, and if we have some time at the end, I'll answer the rest of the questions. Okay, let's talk a bit more about smart contracts. They are executed on something called Ethereum virtual machine. You can think of it as of other virtual machines. So, for instance, if you ever coded in Java, you have JVM. So Java is compiled to a bytecode that is executed on the JVM implementation. Similarly, in Ethereum, we have higher level languages like Solidity, which are compiled down to EVM bytecode, which in turn is executed on Ethereum virtual machine. So EVM is completely isolated from the operating system. It doesn't allow, for instance, making HTTP calls to some other services, connecting other networks. And there's a strong reason for it. The reason for it is that it needs to be deterministic. So imagine that as a part of your transaction, you want to query some HTTP server, some central server using HTTP. Well, different nodes of Ethereum network, while executing this transaction, could get a different result from this server and introduce non-determinism. We cannot allow that, so that's why EVM doesn't even support such operations. You have a set of supported operations, which are nicely presented in something called Ethereum Yellow Paper. And By the way, each of these low-level operations has a set gas that they use, and the way you calculate how much gas a transaction used is by counting those low-level operations. So Solidity is the most popular language that was implemented on top of this Ethereum virtual machine. There are many other languages, but this is you can say that Solidity is the standard one right now. It's object-oriented and statically typed. It supports inheritance, libraries, and you can define your own types there. It looks very similar to, its syntax looks very similar to JavaScript, Java or C++. So learning it is really is not so difficult because the syntax is really familiar. Let me now talk a bit about how we view what's going on right now in the blockchain space. So in early days of internet, we had a client-server model where we build services run on our own hardware, and then we built clients that we often installed on some client computers. Now we have Web 2.0, where we no longer have our own infrastructure. We usually rent it from some providers like AWS or Google Cloud, and our applications are no longer installed on the client computers. We run them in browsers, and we move some of the computation to the browsers. But we still have a client and server model where our services are centralized. In case some data center goes down, it's very likely that the whole service goes down. And some people argue that this is not what the internet meant to be. And with Web 3.0, we are trying to build a better model that is distributed and decentralized. In this model, you no longer have a central server. You have nodes of a peer-to-peer network, which can be located closer to you geographically. For instance, you can be downloading data from your neighbor instead of some server in a foreign country. And in this model, you need blockchain to provide the common state of the service. You also need some distributed storage because, as you'll learn, blockchain is not really the place to store big amounts of data because it's really costly. Someone made a comparison that storing a photo of Lamborghini on a blockchain is more expensive than the Lamborghini itself. So that's the amount of money that we're talking about. So the idea is that we can use distributed storage, and there are many protocols existing like IPFS that work similarly to torrents, which are probably more familiar to someone who didn't have experience with the distributed systems before. And obviously, we run our applications in browsers. Such applications are named decentralized applications, DApps for short. And their main differentiating feature is that they interact with smart contracts that are deployed to some blockchain network. Other than that, you can be viewed as normal internet applications, as normal web apps. So an architecture of such application can look can have 3 layers. You have a presentation layer in the browser, which is managed by HTML and CSS, and also some JavaScript. Then you have a logic layer where JavaScript can also be used, but the majority but the main logic is done in the smart contract. And also you have a data layer which uses blockchain, and also I think I should mention distributed storage here as well. One of the properties of the apps is that they currently can be used by anyone, so you don't need special software to use a decentralized application. Your browser is enough. But in order to make transactions and interact with such application, you need either browser that already supports crypto wallets, or at least you need an extension to the browser. When it comes to browsers with support, I think Opera already does. And the extension that we use the most is called MetaMask. So MetaMask is a crypto wallet that can hold multiple Ethereum accounts. It lets you make transactions, shows you balance of your account, and also balance in ERC20 tokens that Bartek probably mentioned in his presentation. It works with multiple networks, so not only main Ethereum network, but also it works with development networks, so it's useful for programmers when they build applications. The other service worth mentioning is Etherscan, and Etherscan is a website, a service that tracks the state of the blockchain. We call it Block Explorer because it lets you view the data of all of the blocks. It tracks all of the transactions, shows you their status, whether they were already mined or are still waiting for a miner to pick up. Etherscan also enables you to verify a smart contract. What it means? It means that in blockchain, you only store this low-level bytecode of smart contracts. As you can imagine, bytecode looks like assembler. It's not non-readable by humans. That's why Etherscan has a feature that you can upload the code, the source code that was used to generate the bytecode, and it verifies that it's the same. That the source code matches what can be seen on blockchain, and presents it nicely on the smart contract page. It also recently they also even added a feature for you to interact with such smart contracts. So Etherscan can be sort of front end for smart contracts that you can use to make transactions. Thank you for your attention. That will be all for this presentation. Here are the sources of images that I used, and let me now answer some more of your questions. Feel free to ask some more, and I'll try answering the ones that I left previously. Okay, there is one very interesting question by Andre. Why are most the apps working on web, whereas in Web 2.0 users interact more with smartphones? How difficult is it to build the apps on mobile devices? Okay, so first of all, I think we can see some move on mobile devices from applications that you install towards so-called I forget the name, but what I mean are applications that are web apps which look like normal apps on mobile devices. So you obviously can use the apps which are web apps on your mobile device. You would need some special browser for it, but it's totally possible. It is also possible to create native mobile apps that connect to blockchain. Now, what I didn't mention in this presentation is that to run a full blockchain node is really data-consuming task. So you need a lot of storage to hold all of the blockchain data. To give you some idea, right now, I think one of Ethereum implementations called Parity, you need somewhere around 400 gigabytes to run a full node. And full node is not even the node that holds entire history of blockchain. There is a separate node called archival node that does, but full node is enough for you to be sure that for you to be using blockchain trustlessly. Now, this is too much for someone to store on a mobile device. It's also not convenient for people to use such software on their consumer laptops because they don't have 400 gigabytes of storage available. So what do we do in practice? You have two options. First, you can use a node that is provided by someone else, and you have excellent services in Ethereum that offer such feature for free. They are called Infura and Alchemy recently. So such services allow you to send a transaction in a trustless way, but then you do need to place a bit of trust in them because the data that you get from them is can be altered in some way. So you need a bit of trust to use the network in this way. But you are sure that your transactions will never be faked in some way because you still hold private keys that you use to create digital signatures, and sending transactions using such services is completely safe. The other way I mentioned is running a light client. So a third option, I mentioned archival node, full node, and light node. Light node is something we are able to run on a mobile device. This is a node that doesn't store much data. It only stores enough data that it's sure that the block history wasn't tampered with. And for the rest of the data, it queries other nodes of the peer-to-peer network. So when it tries to fetch some balance at a block that was mined like 2 weeks ago, it needs to ask some other node, hey, give me this data, I need this right now. And for the current block, it stores only the block header. So running a light node is totally possible on a mobile device, and you do have Ethereum wallet apps that do this, and you could also create a mobile application that uses a smart contract and runs a light node. If gas price is a set number, how will it change when layer 2 for Ethereum arrives? Well, gas price is not a set number. It's something that's you specify it, but the amount that you should specify is determined by the market. You have for instance, to get to know what gas price you should use, you can use a service by Etherscan that shows you what other transactions mined used recently. I'll be pasting a link to this service in the chat section, so you can take a look. And how does it change when we move to how will it change when layer 2 for Ethereum arrives? The gas price of your transactions will be much lower. And that's one of the points of layer 2 solutions. This is because in layer 2 solutions we batch transactions that happened in this layer 2, and we submit only a batch of transactions to the main Ethereum network. It's a much broader topic, but you can say that transactions should be at least 2 orders of magnitude cheaper. I think it's safe to say that. For more information on layer 2, I strongly recommend Vitalik's article on this topic. I'll try to quickly find a link to it. I think there he goes also through transaction costs and what we expect to see. Andrew mentioned that it's still hard for him to understand. Sure, I didn't even try to explain how a light node works in detail, because I would need to introduce you to the topic of Merkle trees and what are the contents of blocks, and this is too much for a single presentation. I'll try to post some links here after I go through all of the questions. Okay. Where can we check normal gas price? For instance, using the site that I already posted. To deploy our DApp, do we need a real Ether, not a testnet Ether? It depends on the network you're trying to deploy to. If you're deploying to a testnet, and there are multiple of them, you need Ether from this testnet. So for instance, you have Rinkeby testnet, you need Rinkeby Ether. There's Ropsten testnet, and also Kovan. I think these are the ones available right now. And I mostly used Rinkeby in the past for my projects, and I can quickly paste a link to a website that gives away those testnet Ether, this testnet Ether for free. Unfortunately, I don't have a button to mark questions as answered, but if I'm not mistaken, I covered all of them. Okay, I think Mateusz did it for me, and yeah, I'm listening for some other questions. Feel free to ask anything here that's on your mind. And I'll try to look for some resources for Andre. Here's a link to an excellent introduction to all of the different Ethereum nodes. I think I read it recently. They also mention light nodes there and multiple different implementations of Ethereum that you can use as part of your project. I already answered that. You will get this presentation as a PDF later on. Mateusz, do we have a way to forward this PDF? Should we? We will probably. It will probably be possible to post it on Discord. So if you're not already there, you should probably join 0xhack Discord, and we will be posting it somewhere there. Yeah. Okay, if you don't have any other questions, thank you very much, and I invite you to my next presentation, which will start in, I think, 35 minutes. I'll be covering basic Solidity topics there. How did I get to be a blockchain developer? I started looking into this subject on my own. I was studying at Warsaw University of Technology and had to make a bachelor thesis about something. So I figured, why not make a bachelor thesis on a topic that actually interests me? And I studied Ethereum and IPFS as part of it. And shortly after, I got a position at Ethworks and have been working here for almost 2 years. Right now, we're building awesome stuff, and we often hire new people. So I encourage you to look around for open positions. Okay, I think we can wrap this up. Thank you very much again for your attendance, and hope to see you in 30 minutes.